Is the following statement true that A union B all intersected with A is just going to equal to our original set A? Well, how can we know if this statement is going to be true? Well, let's try and draw some diagrams. Let's have a look at these two examples. So when we follow the left-hand side, we should just get the set A back. So let's do that. Let's start with what we have in the brackets. We take A union B, which is going to be basically everything in A, and it's going to be everything in B, right? So it's going to be highlighting everything. And then we want to see, okay, which part of this everything is going to intersect with our A, and we'll label A as orange. So in other words, if what's in brackets is our black and our A is our orange, we're asking what parts are shaded in both colors, and the answer is going to be, well, it's going to be this part. So let's erase the part that doesn't have orange, right? Or doesn't have black. In this case, this one area doesn't have orange, so we want to erase it. And there's no other area we can erase. And yes, the area we're left with having shaded in is just going to equal to our A. All right, what if we have A and B not share anything? They both have very distinct elements. Well, let's have a look. Then we have A union B, which is just going to be all of A. That's going to be all of B. And then we're going to take the intersection of that with A. So we're going to want to take how much of that shares something with A. So how much of this shaded area shares something with A? Well, it's going to be only the part that's also in A, right? So only A shares something with A union B in this case, so we're only left with our original set A as well. All right, let's just do two more examples to be sure that this is going to be true. All right, so what if we have one of them be completely a subset of the other? So let's start by saying A is a subset of B, right? Well, in that case, A union B is going to be this entire thing highlighted, right? And then we ask ourselves, how much of this black shaded area shares something with A? Well, it's going to be just this area, right? Only this area intersects with A. And what are we going to be left with? Which areas have both the shaded in black and the orange part? Well, it's just going to be our set A here, right? We need to erase the other parts that don't share something with A, or the intersection of A and, or the union of A and B, which is going to be that we need to just erase this section right here since it doesn't share anything with A. Let me actually rewrite that to look a little nicer. There we go. Okay, so in this case, we're also getting A back. What about the case where it's the other way around, where B is a subset of A? Okay, well then A union B is just going to be this entire section shaded in, right? It's going to be all of A and all of B. And then we want to ask ourselves, well, what part of this shares something with A? What part of this black area is in A? Well, all of it is in A, right? So we just need to highlight all of it in orange. And there we go. We find that we get the set A back because the parts that have both orange and black is basically the entire set A. So it looks like that the statement is going to be true, so let's go ahead and prove it. So to prove this, we need to recognize this is going to be an equivalence, which means we have to prove that the left-hand side is a subset of the right-hand side and the right-hand side is a subset of the left-hand side. Why do we do this? Well, logically, we can say that everything here has to be here, and everything here must be there, right? That's what it means for two things to be equal, and that's exactly what a subset is. So we need to prove the following two conditions. So we need to show that both of these are true. That is what we're going to be proving. We're going to be proving this is true, and that is true. And once we've shown that, we can then conclude that this must be true. So that's going to be our setup of our proof. So how do we start proving this? Well, we have to recognize this is a for all proof because this is for any sets A and B, right? And for any is a for all. So how do we start our proof? We start with a let. We say let A and B be sets. Fantastic. Now we can get into our first case, which will be showing the left-hand side is a subset of the right-hand side. Okay, so to show that the left-hand side is a subset of the right-hand side, we need to show that every element here is going to be also in this set. So every element in this set has to be in this set. And how are we going to do that? Well, if we can show that any element, for example, x will represent any element in this first set. If we can show x will always, or is also an element of A, then we've shown that since any element here is here, then we've shown all elements here are here, meaning this is a subset of that, right? So how are we going to do this? Well, let's break apart what it first means for x to be an element of A intersect with open bracket A union B close bracket. This means that x is the subset of A, and that's where this comes from. X is an element of A, or X is an element of B, right? That's what this means. You can put brackets around this so you can more clearly see. Or actually, a better way of saying this a little more explicitly is to say that X is an element of A and X is an element of A union B. Then we can break apart what it means for X to be an element of A union B. This means X is an element of A or X is an element of B. Fantastic. Okay, well, we already know that this has to be an element of A because it's going to be an element of A by this condition. So we just have to go to these two cases since we have an OR. So what do the two cases mean? It means in our proof we're going to say, well, X is an A. Maybe we can actually immediately jump from here to here. But I'm a little hesitant to do that right now. So let's just stick with this. So we have two cases. So we'll say, okay, if X is an A and X is an A, then obviously X is going to be an A. Okay, if X is in B, then we know X is in A and X is in B. How do we know X is in A? Well, that's because this X in A condition carries over to both of these ORs, right? So when we're saying if X is in A, we're saying if X is in A and X is in A. If we're instead saying if X is in B, we're saying X is in B and X is in A. So this still shows us that X is in A. Okay, so I think we have our sketch of our proof down. Let's go ahead and try and show that, or put that more precisely into words. Okay, so how do we start this proof? We start by supposing our representative element, right? We can say, suppose X is going to be an element of A intersect with A union B. Fantastic. Now we can say, okay, well, what does it mean for X to be an element of this set? Well, it means that then X is an element of A and X is an element of A, or actually, right, we're being very explicit, we're saying and X is an element of A union B. Now, I think you can, I'm thinking you can immediately go from here and say, well, because it's always going to be an A, it's going to be an A. But I'm going to be a little more explicit. I'm going to go with the two cases here just to really drive it home that this is going to be an A. We will say that, so if X is in A, then, then obviously, right? Yeah, okay, yeah, then we'll say, I think we just immediately jump to here, I'm thinking, if X is an A, right? Then, yeah, I don't think I have to say X is an A and X is an A. I think if I just say if X is an A, then we can just immediately jump to saying then of course A intersect with A union B is a subset of A. If X is in B, then X is going to be an element of A and X is an element of B. So since X is still an element of A, then A intersect with A union B is going to be a subset of A, right? I've kind of just said that if it's an A, it's an A. If it's in B, it's still going to be an A, right? That's what I'm trying to get across here. Okay, fantastic. Now let's prove our second case. Okay, so for our second case, we want to show the right-hand side is a subset of the left-hand side. So we need to start with our A, and we need to show that any element here, we'll call these elements Y, must also be in our other set, A intersect, open bracket, A union B, close bracket, right? Which means if we can show that Y can be in both, then every element in A is going to be in that set, which makes A a subset of that set. So what does this mean? Well, this means that since A is an A, then obviously, Y is an A, not A is an A, my bad. Then Y is going to obviously be an A union B. And since and we can say and Y is an A, right? Like, that doesn't change the fact that Y is an A. Then we can say when this is true, obviously that leads to this. I think that's fairly straightforward. There doesn't seem to be any trickery here that we need to think about. Yeah, okay, I think this should be fine. So let's go ahead and write this down. So we start by supposing our representative element Y. We'll say suppose there exists some y that's going to be an element of A. Fantastic. We can then say, then y is an element of A, and y is going to be an element of A union B. Fantastic. And actually, we can continue that sentence and say, so y is an element of A intersect with A union B. There we go. Thus, and now we can conclude what we were trying to prove, A is a subset of A intersect with A union B. Fantastic. Okay, so we've proven both of our cases to be true, so now it's just left to write our conclusion. So let's go ahead and do that. So we can say that since A intersect A union B is a subset of A, and A intersect with A is a subset of A intersect with A union B, then of course they're equal to each other, which means we're just going to rewrite what we wrote at the very beginning, our statement that we're trying to prove, which is A intersect, open bracket, A union B, close bracket is equal to A. Fantastic. So there we go. We've proven that this statement up here is in fact going to be true.